Welcome back to Catalyst Grid. My name is Kingsley Amufua, lead scheduler with DC Nordics. Today we confront the defining engineering challenge of the next decade, AI-ready infrastructure. This is where we ensure the machine never stops. We are moving from the high-voltage generator yard into the heart of the data halls. This is Series 2, Episode 12, AI-ready, GPU clusters, 400 VDC, and liquid cooling. Building the machine at hyperscale requires absolute, uninterrupted continuity. A standard data center rack consumes 10 to 15 kilowatts. Enterprise servers, storage arrays, network switches, all cooled by simply moving air past them. This has been our baseline for 40 years. A modern AI GPU cluster rack consumes 100 kilowatts, 10 times the power density, 10 times the heat, and air cooling cannot remove that thermal energy fast enough. Hall's DH3 and DH4 are designed to solve this problem. Look at the evolution. Since the 90s, rack density has scaled predictably, moving from 1 kilowatt to 15. But the AI revolution has shattered this linear progression, demanding a vertical shift in engineering capacity. Air cooling reaches a physical ceiling at approximately 25 to 30 kilowatts per rack. Beyond this point, the temperature rise of the air exceeds the thermal limits of the electronics, regardless of how fast we move it. A single modern AI accelerator chip has a thermal design power of 700 watts. One training server carries 8 of these chips. That is 5.6 kilowatts from GPUs alone, before we even account for CPUs and networking. A fully loaded GPU cluster rack with 8 servers reaches 44 kilowatts from GPUs alone. Real-world clusters are hitting 80 to 100 kilowatts today, and the next generation will push us toward 120 kilowatts per rack. Liquid cooling is no longer optional. Before we address cooling, we must address how power reaches these racks. At 100 kilowatts per rack, traditional AC distribution paths become a major source of efficiency loss. We must change the architecture fundamentally. In a conventional data center, power flows as AC from the utility through the UPS and PDU to the server power supply. This requires 3 separate conversion stages, losing approximately 12% of total energy as waste heat. FULCRUM's 400 VDC architecture in DH3 and DH4 eliminates 2 conversion stages. Power flows from the UPS rectifier directly to a 400 VDC busbar and then into the server. This halves our conversion losses to just 6%. At 21 megawatts per hall, this saves approximately 1.3 megawatts of power that would otherwise be lost to heat. This contributes roughly 0.03 to our overall PUE reduction. It is efficiency by design. Industry alignment is already here. All major AI infrastructure server vendors now offer 400 V DC power supply inputs as standard, making this hyperscale topology the new industrial reality. Now let's talk about heat removal. The rear door heat exchanger, or RDHX, is a liquid-cooled coil mounted directly on the rear of the server rack. It is the gatekeeper between the server exhaust and the data hall. Hot exhaust air from the servers passes through the coil as it exits the rack. Chilled water flowing through the coil absorbs the heat, removing it before it ever enters the hot aisle. The result is a thermally neutral data hall. Our RDHX units can handle up to 120 kilowatts per door, covering even the most dense projected AI workloads. We operate on a standard chilled water circuit with 16-degree supply and 26-degree return. Serviceability is maintained through flexible hose connections at the top of the door. Quick-release non-drip couplings allow technicians to open the rack door for maintenance without disconnecting the cooling circuit or risking a leak. Flow is managed by per-rack proportional control valves. Coolant flow adjusts dynamically to match the rack's thermal load, preventing overcooling and significantly reducing the risk of condensation on the coil. Every RDHX unit is fully integrated into our DCM. We track supply and return temperatures and flow rates at the rack level, providing our operations team with total visibility into cooling efficiency and performance. Condensation is the most critical operational risk for any liquid cooling system. If chilled water supply temperature drops below the hall's dew point, water will condense on the coil and drip onto live electronics. That is catastrophic. To prevent this, FULCRUM's controls maintain the chilled water supply above the dew point at all times. A mixing valve blends return water with supply water, holding a minimum safe delivery temperature of 16 degrees. The Coolant Distribution Unit, or CDU, is the interface between the building's secondary chilled water circuit and the rack-level RDHX systems. It is the brain of the row-level thermal management. Each row of GPU racks is served by a dedicated CDU. It conditions the water to the precise temperature and pressure required before distributing it through the row manifold. This localization provides superior control. The CDU contains integrated flow control, pressure regulation, and leak detection. At 100 kilowatts per rack, losing cooling is a thermal emergency. Our CDU's automatic isolation systems are designed to respond within 30 seconds of any leak event. By combining high-density power delivery with precise liquid cooling, we ensure that Hall's DH3 and DH4 can support the massive computational demands of AI training while maintaining absolute operational stability. It's time for the series signal. The transition to liquid cooling at the rack level is not a future planning item. It is a current, non-negotiable design requirement for any AI-ready data center. If your facility is being designed today without RDHX or direct liquid cooling provisions, it cannot serve the dominant GPU workloads of the next decade. Prepare your infrastructure now or risk obsolescence. In episode 13, we look at the unique challenge of phased campus delivery. How do you protect a live Tier 4 facility while the Phase 2 piling rigs are drilling just meters away? The logistics of continuity. Thank you for joining me for this deep dive into AI GPU infrastructure. Building for the future requires courage and absolute engineering discipline. I am Kingsley Aimufua, building the future of power. Don't forget to subscribe, like, share, and comment below. Your engagement helps us build a stronger community for the engineers building the future. I'll see you in the next episode. Thank you for watching Catalyst Grid, building the machine at Hyperscale. Keep building, stay safe, and goodbye for now. This technical documentation is intended for professional use within the DC Nordics and Cloud Core engineering networks. Confidentiality status remains active for all GPU cluster specifications presented. For technical inquiries regarding 400V DC distribution or RDHX integration, please contact the DC Nordics Project Management Office. Building the machine at Hyperscale, Phase 1 and 2 integration active. Thank you for your commitment to engineering excellence. Catalyst Grid Series 2 will return with Episode 13, Phase Delivery and Operational Continuity, Project Update complete. This concludes Episode 12, Professional Technical Documentation produced for the global hyperscale community, Building the Machine, Catalyst Grid, Conclusion.